Rohit Kumar Singh, and I'm the teaching assistant for this course, Statistical Mechanics. And this is the 9th live session for this course. And today I'll just quickly recap some of the concept of quantum statistics. So far we have been dealing with classical statistics or the statistical mechanics applied to classical systems or semi-classical systems. But in real world we have when you go to low temperature or high density, you always encounter quantum mechanics, right? So there the statistical mechanics that we have been learning so far will not be applied, because you have seen that we have always used this phase space and this density function as a function of q and p, position coordinate and momentum coordinate. But in quantum mechanics we no longer have position position and momentum coordinates, right? We have the operator, so we have to reformulate everything in order to incorporate the quantum mechanics inside the statistical picture. So to do that, so far we have we have discussed classical systems, right? Classical or semi-classical systems, which are always non-identical, right? So we can tell each of the particle in the system apart, non-identical, and also if it is distinguishable, then it is classical, we will call it classical, and if it is indistinguishable, we can call it semi-classical, right? But so far they have been non-identical. But what about if we have identical systems? So if you have identical system, then we have to consider quantum statistics. Okay, and so to see how our so our goal in statistical physics is to calculate the expectation value or the average value of some function like energy or entropy at the end, right, for a system. And for that we consider an ensemble of the system, which are mental copies, okay, of the same system having different energy or different number of particles, right? So there are so far we have studied 3 such ensemble: microcanonical, canonical, and grand canonical. But the goal is always to at the end to calculate expectation value of these functions. Okay, so if we have a quantum system, identical system, which is which cannot be described by a classical picture, then how do we consider how do we construct the ensemble and basically the partition function? Because here the partition, we cannot write simply the partition function, because now all the particles of the system are identical, right? So it's we cannot tell E1, E2, E3 apart, right? They are all identical. So instead, what we can do is we can consider the quantum mechanical picture, right? So you know, in quantum mechanics, we can represent a wave function uh, in different representations. Like uh, you can take orthonormal functions, set of orthonormal functions, and you can describe the general wave function uh, as a sum of you know those orthonormal functions. So let me remind you what I am saying. So I am assuming all of you know a little bit of quantum mechanics, okay? Uh, if you don't, if you have never studied quantum mechanics, let me know. I'll so that I can, I mean, try to give you some detailed picture of quantum mechanics. But I'll assume that you all have some knowledge of quantum mechanics. So yeah. So basically, we have in quantum statistics. Let's consider an ensemble of n identical systems, okay, where this n should be very large, okay. Now at any time t, uh, the state of the system, the physical state of these various n systems is given by the wave function, right? So let's call it psi, and this wave function is it is function of position and time, right? Space and time, and k is equal to 1 to up to n. So you have n identical systems, okay. All of them are characterized by this wave function, okay, psi. Now if you have a wave function, you know that in quantum mechanics all the wave function, I mean the time evolution of the wave function is governed by the which equation? Do you guys know? Time variation of wave function. So d psi by dt. Schrodinger equation, right? Which is simply this is the Schrodinger equation, where h is the Hamiltonian of the system, okay. Okay, and also we know that any wave function, so any general wave function, so let's only consider the time variation, okay. So any general wave function can be written as a sum of a complete set of orthonormal function, which are called basis. So this is n. So n goes over from 1 to infinity phi n, where phi n is complete set of orthonormal functions. Do you guys know this concept? So this is true for all the, all the k systems, for all uh, k systems. Okay, so you have k equal to 1 to up to n systems. Okay, and for each systems the wave function can be written as the sum of, orthonormal functions with some amplitude an. Okay, now this an is what? So it is a probability amplitude, right? So an is, so this has so far nothing to do with statistical mechanics. I'm just talking about quantum mechanics. Okay, so this is basic quantum mechanics that you all have studied. So an is the probability amplitude for the various systems, various k systems of the ensemble to be in various state phi n. Okay, so phi n is the orthonormal function which can be anything. So later we will see that we can take the energy eigenfunctions, for example, as our phi n, and so on. So this is to make things simpler, right? uh, Let me know if you have any doubt till here. So so an is the probability amplitude, and then an square is just the probability, right? So it is the probability that if you are at any time t, if you're going to measure, if you're going to check the system, okay, it is the probability that the system will be found in a state phi n. Okay, probability to be in phi n state. Is it okay? And as you know, the sum of all such probabilities should be 1, right? So this is the normalization criteria of quantum mechanics. So if you sum over all such probabilities, it should be 1, right? I mean, the system has to be in some state, right? So this is a normalization criteria. Is it okay? So this is just quantum mechanics. You have a system described by this wave function. So there are k systems, there are n systems, okay, characterized by this indices k, okay, and all of this system follow this Schrodinger equation, right? All of the wave function of the system, and all of these wave function can be decomposed as a sum of orthonormal functions. Okay, so this is called representation of a wave function. Okay, and this this constant an, it is the probability amplitude for the system of the ensemble to be in various state phi n. Okay, and this phi n is also called basis, and the square of this amplitude is just the probability of the phi system, the probability of the system with wave function phi, wave function psi to be in a phi n state, okay, in one of the state, and sum of all these probabilities is equal to 1. So now we have a quantum mechanical picture. Okay, now we can go back to statistics. So so when we were studying statistical mechanics, we considered a density function. Do you remember the density function as a function of q and p? Do you guys remember it? What was the definition of this density function? Mm-hmm. Anyone? So this density function has this interpretation that at any time t, uh, so so this was basically a probability density. So at any time t, what is the probability if you are measuring if you are going to measure the energy of the system, it will be in a particular energy En, and I mean it will contain energy En. So and we found that this probability is proportional to this quantity, right? And we call it PR. So this is the probability density. Actually, this is probability density. You have to multiply by the you know the phase space volume dW to have the probability. Anyway, so similar to that, in quantum statistics, we have a density operator. So you know that in quantum mechanics, every function becomes an operator, right? So here we have a density operator, and we will see that it later it will have the same interpretation as the density function. So we denote operator like this, okay, and it has two indices. So I mean it is written like this, and it is defined as this quantity. So 1 over n sum over, and where is this sum? Is sum goes over all the system of the ensemble, okay, sum over am kt. So the probability, this is the probability amplitude that we have from earlier, and another probability amplitude an, and its complex conjugate, okay, and we know that both are functions of time. So this here the density operator is just a average of this quantity, okay, over all the ensemble, over all the system in the ensemble. So now I mean this is very unintuitive to understand what this density operator really means. But to simplify things, let's put m equal to n, okay, then this density operator become rho nn, and you have just this, right? Sorry. And what is this? This is the probability, right? Probability of psi to be in phi n state. So basically rho nn is the ensemble average, because this summation is over all the system of the ensemble, right? So this is the ensemble average of probability an square, right? So this is so if you put n equal to m equal to n, you get the average of the probability. Okay, and what does this represent? Okay, so we can say that rho n represent the probability that a system chosen at random from the ensemble, chosen at random from the ensemble at time t is found to be in a state phi n. Okay, now you see, as I told you, this density operator is more or similar to the density function that we had in classical statistical physics. So density function density function represent the probability of finding your particle in a given state, in a having a particular energy En, right? And here the density operator tells you that it is the probability that a system chosen at random is found to be in a state psi n. So both are similar concepts, right? Do you agree? And if you sum over all such all these density operators over the n indices, so this n represent the orthonormal functions, okay, which are infinite basically. So what do you get? So let's do the summation. So sum over n, you have 1 over n, then you have sum over k, okay, a n k star, right? So yeah, so this is just, as we saw, this is just the probability, okay, and we know that this is equal to 1, right? Sorry, no, this is not equal to 1. Wait. We can switch the summation, right? We can first sum over we can first sum over k, take a 1 by a naught, yeah. So this is equal to 1, right? It is just the sum of probability which should be equal to n, which is equal to 1. So 1 over n into 1, right? So 1 by n sum over 1, k is equal to 1 to n, so 1 over n into n, cancel out, gives you 1, right? So you see, this is a normalization criteria. We also saw it when we did this, we got 1. Sum of all the probabilities should be 1. Similarly here also this is 1, okay. Are you guys able to follow? Now, in classical picture, we had Liouville's theorem. Do you remember the Liouville's theorem in classical picture? What we had? We had this d rho by dt is equal to del rho del t plus rho h equal to 0, right? So similarly here also in quantum mechanical picture also we have this Liouville theorem, which is given in operator form. Okay, this is the Liouville quantum mechanical analog of Liouville. But so what does it basically say is, if your if given system, I mean if the given system is in equilibrium, okay, uh, then the corresponding ensemble must be stationary, right? And so the time variation of this density operator should be 0, okay, if system is in equilibrium. And so so these two operators commutes, okay. Hamiltonian commutes with so this is called commutator. Do you guys know? This is the expression for commutator in quantum mechanics. So this is just this quantity, okay. So if two operators commute, what do we say? Anyone does anyone remember what happens when two operators commute? Hello guys, do you know what happens? Anyone remember from quantum mechanics? Okay, so if you don't remember, let me remind you. So if two operators commute, what happens? They
have the same eigenvalue.
yeah, they share the eigenvalues, right? Yeah, right. And I mean, yeah. So then these psi that we are talking about, these wave function that we are talking about, right? They can be they are also energy eigenstate, right? Because basically the operator, the density operator commute with the Hamiltonian, so both will share the same eigen functions, okay. And this also means that so this we can also write it like this. So this Hamiltonian sorry, this density operator will be a function of Hamiltonian basically, okay. Or we can write like this. And one more thing is that the time variation of Hamiltonian will be 0, okay, from here, as you can see. So system is basically the ensemble is stationary. there is no change in energy. I mean, there is no system is in equilibrium, so energy is constant. I mean, Hamiltonian is constant, so energy is constant, because this Hamiltonian operates on, when operates on the wave function, gives you energy of the system, right? So at the end, the energy of the system is constant. It's not changing. Okay, so this is something to remember uh, for equilibrium, for systems in equilibrium. Okay, and then you can so as I mentioned, so uh, the basis function that we were considering, they can they, they can be the eigenfunction of the Hamiltonian itself. So basic so can be also the eigenfunctions of Hamiltonian, because as we mentioned, the both commutes, so you can write Hamiltonian like this. So the I mean, the Hamiltonian matrix will contain elements like this. Okay, this is Kronecker delta, and the density function you can write like this. This, oh no, I'm not saying H is equal to E. I'm saying when H operates on your wave function, it gives you this, right? So if this is, if you do time variation on both sides, so that if this is 0, then this is also 0, so En is equal to, En is constant. That's what I am saying. Is it okay? Yeah. Now we come to our most important part. So okay, we have found a way to find the probability that a system chosen at a random at random at certain time is found to be in a state given by phi n. Okay, and we got this expression of the density density operator, right? This expression. But now what we want to do is we want to calculate average of some expectation value or average of some function, right? Expectation value. So now all these function will be represented here as an operator, right? Because we are in quantum realm. So this expectation value will be simply so from quantum mechanics, simple in quantum mechanics, if you have uh, okay, so yeah, so if you in classical mechanics, if you want to calculate average of energy, what do? You sum over all the energy of I mean sum over all the ensemble and uh, divide by the number of system in the ensemble, right? Now here what you, here this is not valid, right? Or in general, if you have a function g, then you sum over this, whatever this, I mean, so suppose if this is entropy, you sum over all the entropy of the system in the ensemble and divide by n. So this is how you take average classically. But here if you want to take average, what you need to do? summation you have to do on over all the system in the ensemble, right? But here you have to consider this, the wave, I mean the expectation value. This is how you calculate, right? Is this okay? From this is from quantum mechanics. And this is an integral, right? So state k star g psi k d tau. So this d tau is the you know position, I mean the volume element in the coordinate space, right? So when I was I mean, just to avoid confusion, when I wrote this wave function decomposition in terms of the orthogonal functions phi n, this probability amplitude is given by this integral, right? This you guys know. Sorry, d tau. D tau is volume element in coordinate space. Okay. So if you are taking average, you have to take average like this, right? Now we can further write it down like this. So we can now write wave function. I mean, we can write wave function as a decomposition of this using this decomposition formula, right? So let's write it in terms of phi n. Okay. So what do we get? Integral a n k star phi n star g a m k phi m, right, d tau. And further you can write it like this. So let's not write the integral. A n k star a m k. So we introduced a matrix element g n m, and this g n m is equal to the integral inside. Okay, is this fine? The sum is this is a double sum over n and m, and further we can simplify it like this. So you remember this is the density of operator rho mn, yeah, and then you have g n m, right? And what is this? This is just summation over m rho g, right? So the n is summed over. So n is here. I mean, both m and n are repeated indices here. So we can sum over n, right? So these are two. Basically, this is the multiplication of two matrices and then summed over m. And this is nothing but trace of this multiplication of two matrices. Okay, so you get this formula. So if you want to calculate any average of any function or any operator, what you do is you just take trace with the density operator of this function. Okay, now if you choose your operator, the general operator G, as unitary operator, then what happens? So if you put here in this equation, so average of unitary operator is just 1, right? And then trace of rho. So you see trace of this density operator is just 1. Okay, so this is another very interesting result. So as I mentioned, what happened now is the density function that we had in uh, you know in classical mechanics has become the density operator, right, which is given by which is given by this. And so so classically you had this expression, right? This was and below you had the partition function, if you remember, right? Now in the operator form, what will happen is uh, you will have to consider uh, you will have to write the orthogonal in terms of orthogonal functions phi n. So same thing, and then the partition function qn. Okay, so you take qn outside, you can write like this. Right, and this is just the unitary operator, right? So you get this expression for the density operator. Okay, which is and okay, and the qn is just the as we saw here that so qn is just the sum over classically, yeah, but in quantum mechanics qn will be just the trace of this function. Okay, so the density operator finally given by this formula. And similarly, average of any other function will be given by this formula. So I am considering the canonical ensemble only. Okay, here this can be generalized into grand canonical ensemble also. Just you have to consider the fugacity. Now this n here denotes that this averaging is over an ensemble, okay, with fixed n. So this averaging is over an ensemble with n fixed, keeping the n fixed. So these are the formula that we need to keep in mind if you want to calculate any average of any quantity in the problems. Okay, and these are very similar to what we have in classical mechanics. There we have the summation, here we have a trace. Okay, so is it fine? Did you guys follow? Let me know if you have confusion at some point. So did you understand why we write like this, our density operator? We wrote it as a so we cannot, the operator we need to write it in some basis, right? We have to represent it in some basis. So we use just the phi n basis, okay, which are our energy eigenstate also, as we saw earlier. So these are our phi and our energy eigenstates. I mean, eigenfunctions of Hamiltonian are called energy eigenstate. So that's why we can do this. We can take the Hamiltonian ort, and this is basic quantum mechanical calculation. If you have confusion here, then please let me know. I will try to explain more. Is it fine with everyone? So that I can move on with some problems. Please let me know. Hello? Okay. So if it is okay with everyone, let's solve some problems based on what we have seen so far. So okay, so first problem we have here is, so this is a very basic problem, very simple system. So we have an electron, okay, in an external magnetic field B, and the Hamiltonian is given, okay, and where this sigma is the Pauli spinor operator. So Pauli matrices. So you guys know that Pauli matrices are given by this sigma x, sigma y is 0, minus I 0, and sigma z is given by 1, 0, 0, minus 1. Okay. Okay, so and mu b is the Bohr magneton. It's a constant. Now we have to find the density matrix in the representation of sigma z. So what does this mean? Density matrix. So we have to basically use this equation, right? So what we have to find is sorry. We have to calculate this for the given system. Okay. How do we do this? So first let's so here the here it says in the representation of sigma z, okay, So what does this mean? So this basically means that we have to assume that the applied field, the magnetic field, is in the direction of z-axis. Okay, and if we consider that, then our Hamiltonian is simply, so here Hamiltonian given is polymatrix is equal to the density. No. Uh, polymatrix Polymatrices are spin operators. Okay, so so if you have a spin system 1001, okay, so these are the eigen functions of polymatrices basically. Okay, so polymatrices are polymatrices are operators, spin operators basically, and the eigenfunctions of these polymatrices are these spinors. Okay, so it has nothing to do with this density matrix. Density matrix is a different thing, like I explained here, right? So the density, so basically, density matrix is, remember this definition always. Okay, it represents the probability that a system chosen at random from the ensemble is found to be in a state phi n. Okay, now this state can be any it can be a eigenfunction. So if we are considering an eigenfunction representation, energy representation, then the state will have energy En. Okay, and so in the energy representation, this density matrix become equivalent to the probability density that we had in classical statistics. Okay, so don't get confused. This polymatrices are different thing. It has nothing to do with statistical physics. It is a quantum mechanical just matrix operator. Okay, and here we saw that the Hamiltonian is given as a function of this polymatrices. So how can it be the density matrix? Okay, so if we consider the magnetic field in the direction of z axis, then the Hamiltonian becomes, so sigma dot b this will be sigma z, okay, b, or we can write it other way around. Okay, and now this is our Hamiltonian. Okay, and we have to now find the this quantity, right? And this will be equal to minus beta mu b, sorry, it will be then plus minus plus b sigma z. Okay, now how do you evaluate this? So this is the numerator of this trace. How do you evaluate this? Any idea? So you will have to take the expansion, taking log on both sides. No, it won't work. So this is so because see, this sigma z is operator, it is not a number. Okay, it is an operator. which is given by here, this by this is a matrix, right? So how do you calculate the exponential of a matrix? Do you remember? You take the expansion, right? So you just, so this, so suppose this whole thing is x, some x operator, okay? So xn n factorial, right? And then, so if you take summation like this, what happens is you get beta mu b. So this is the constant sigma z n, sigma z to the power n, okay, which will be equal to, so let's take this thing outside, sorry, in keep it all in capital, yeah, okay. So if you will expand, if you expand it, let me write below. First term will be simply so this is 1, right? First term will be sigma z, then the second term will be by 2 sigma z square, third term, similarly third term will be, you know, sigma z cube, and so on, right? But now you see here from this equation, sigma z square, what is sigma z square? So you multiply it with another sigma z, and what do you get? Can anyone do this calculation? I am doing it. Sigma z square is identity, right? And again sigma z cube, what you will get? You get the same thing, right? So the even will be identity matrix, the odd one will be again sigma z, like this. Am I right? Please check. So yeah, so finally what you will get is so okay, so I'm not going to, I mean, write explicitly, it will be messier, but okay, I'll write the result. So finally you will get this. And here 0. Okay, so just you can verify it. Okay, and the trace of the same quantity will be what? So trace of this matrix, it is just sum of the diagonal elements, which is ub plus minus ub. Okay, so then finally the density operator is given by this formula. Okay, oh, how can you make this in matrix form? You already have matrix, right? Okay, so let me show you how briefly. So this thing, what you have here is simply multiplied by sigma z. See, so sigma z, what you have, sorry, 1 0 0 minus 1 plus sigma z square, we saw it is just 1, I mean it is just identity matrix. So you have again 1 0 0 1 by 2, then you have the sigma z cube you found, it is equal to sigma z again. So then you have this term again, right? But here 3 factorial is there, right? And similarly so on. So now you can multiply these in matrices, and what you have here is beta mu b plus beta mu b by 2 plus beta mu b by 3 cube, and so on, right, in the first element. And this will give you this, and similarly on the this element here, you have to sum this from, starting from this minus plus minus, and that will give you this term. Do you understand what I am saying, or should I do it more explicitly? So let me try. So what I am saying is, this you have, then 0 0, and then here you will have minus beta mu b plus beta mu b by 2 minus beta mu b by 3 factorial, and this term is nothing but this exponential of minus beta mu b, right? So there you have this, so that's how you get this matrix. Is it okay? Who was asking? Devasmita, is it okay? Okay, thank you. So yeah, so this is the density matrix that you will obtain, and then okay, so that's what we wanted to calculate here, right? So the correct option is this second one. So everyone understood, right, what we did? It is just simple calculation. Okay, now the second question is, we have to write the same density matrix in the representation of sigma x. Okay, so now we will have to consider the magnetic field in the direction of sigma x. I mean, so see the, okay, So you might be confused. How can we assume? How can we assume any direction of magnetic field? Magnetic field is pointed in some particular direction, correct? You guys have not asked this question, but so I'm asking this question in on behalf of you to myself. So you might have this confusion. So here I assumed that the magnetic field is in direction of z axis, okay? So that we got this sigma z here, because the question asked the rho in the representation of sigma z. So we wanted to have the sigma z in the equation, okay, in the Hamiltonian. So we assumed the magnetic field in z direction. Now the second here problem says the density matrix in the representation of sigma x. So now we will assume that the magnetic field is pointed in direction of x. Okay, we can assume that in space there is no coordinates, right? We can assume any direction as x, y, z, right, to solve the problem. It is okay. It is just a convention. We can use it to our convenience, right? There is no issue. So if we do that, then our magnetic field will be then our Hamiltonian will be given by this formula, sigma x, right, where sigma x is simply 0, 1, 1, 0. Okay, and then you can do the same thing. So you have to calculate this numerator, and then you take the trace of the same numerator. So so should I do this, or you guys will be able to do it? Do you guys want to give it a try? So you have to find out this thing, okay? So just give it a try. It's very simple. If you guys will not be able to do it, then I will do it in the next session, okay? So I'll leave it as an exercise. It's very simple. Is it okay? Should I leave it as an exercise? So you again have to find this thing, okay? So okay, you guys will do it. Okay, great. So yeah, fine. Then let's move on to the next problem. So now here the problem says, taking z axis along the direction of magnetic field, the average of sigma z in the above two representations are respectively. Now here comes the average thing. So we know what is the how we calculate the average. We take the trace with the density matrix and then divide by the trace of the density matrix, right? This is what we defined as the sorry, oh no, not with the density matrix. Trace with the trace of this function multiplied by this, and then trace of exponential of minus beta h. Yeah. Okay, and here we have to find the average value or the expectation value of sigma z. So we have to find this. This we have already calculated. The denominator we have already calculated. So we don't have to worry about it, right? We have to calculate this thing. So trace of sigma z minus beta h. So we have to take z axis along the direction of magnetic field. Okay. And what that gives us as Hamiltonian, it gives us this, the sigma z, right? So basically this trace becomes e to the power sorry this trace becomes sigma z e to the power minus b minus gets plus beta mu b sigma z. Fine. So this is what we have to now calculate. And which is very simple, right? So I mean we have already, so let's keep this sigma z like this. Okay, this we have already evaluated here, right? This is the matrix, this we have evaluated, right? So then sigma z, and here we write the matrix that we evaluated already, which is e to the power mu b beta mu b and minus beta mu b, right? And then trace of this sigma z is given by 1 0 0 minus 1. So we have to first take the matrix multiplication and then just take the trace. So trace of, so let's multiply it. What will be the value? So this is just mu b right? Here it is 0 0, and then multiplying this gives you 0 here, and multiplying this gives you 0 here, and then this gives you minus beta mu b, right? And then you take trace, that means you sum the diagonal elements, you get this minus e to the power minus mu b, right? And then sigma z, average of sigma z is this thing. So on the numerator you have trace of this, and then in the denominator you have trace of e to the power minus beta h, which is this quantity, right? We calculated. So just the same quantity with plus sign in between. And do you recognize this is very, I mean this is tan h beta mu b p, okay? And similarly you can calculate the sigma x once you have once you calculate this in the representation of sigma x. Okay, so this also I leave it as an exercise for you. Is it fine? Hello guys? Okay, great, thank you. Then let's go to the next problem. Okay, so here we have to find out the partition function of a two-level system governed by this Hamiltonian. Okay, so partition function, as we saw, is just the trace. What is the partition function? Sorry, it is the trace of this, right? Now how to evaluate this? Here the Hamiltonian is given, so how to evaluate this? Any idea? So one thing you have to do, so this is, no, this is a very, this is the same problem that we considered earlier. Okay, there also we had a two level system, spin up and spin down, right? But here the Hamiltonian is different, it is not the Pauli matrices, right? So one way to evaluate this is, yeah, you can do the same thing that we did there. You can you can evaluate this quantity. You can write it as a matrix form, right? Then take trace. But problem here is this, that we don't know the representation of this Hamiltonian. This Hamiltonian, uh, so there we had, there the Hamiltonian was, represented by this sigma z or sigma x, right? We had a representation, standard representation. Here we don't have such representation. But what we can do is, we can calculate the energy eigenstate or energy eigenvalues for this Hamiltonian, right? And that will be, so I am showing you another way to solve, such kind of problem. Okay, so the earlier problem could also be solved this way. Okay, I will show you. It is very simple to see when I will write down. So you can find the eigenvalues, and eigenvalues will be the, the energy that this system can take. And what is the partition function? Partition function, our Qn is basically sum of this thing, right? So if you find the En, the energy eigenvalues, we can find our partition function without having to do this matrix, calculation. You just have to find the eigenvalue of this Hamiltonian. This you can also do here, right? So you have this Hamiltonian, you can find the energy eigenvalues, and then you can see that it will be the same thing. So since you have a since you have a electron in an external field, you know that this you can calculate the eigenvalue of this matrix, right? This is your Hamiltonian. You can calculate the energy eigenvalues, right? So the energy eigenvalues will be simply, you will see that they will be simply plus minus mu b. Okay, so then your partition function will be this thing, right? So that we can do here also. Is it fine what I am saying? But when you have to calculate the density operator, then you will have to find out this matrix by doing the tedious calculation. But for partition function, we don't have to deal with the matrix. We can just find the eigenvalue of this corresponding to this eigenvalue, corresponding to this Hamiltonian, and we can put in this equation. Okay. So, is it okay what I am saying? Do you guys follow? Okay. Yeah. So, yeah, thank you. So, let's find the eigenvalue. So, you guys know how to calculate eigenvalue for Hamiltonian, right? You take this determinant for some constant lambda identity matrix, put it to 0, right? So determinant of gamma minus delta minus gamma, this matrix minus lambda 1 0 0 1 0, and this will be okay. So can you repeat it again? Okay, so okay, let me do this. So what I'm saying is here the problem asks us to calculate the partition function only. Okay, partition function, not the density operator. Now what is the partition function formula? So this is the partition function formula, right? And also the also this formula of partition function we know from earlier. This is also valid. Okay. Now I am saying that this and this are same thing, right? If you have your wave functions, okay, which are which are the which can be written as an eigen we can be decomposed in the eigen functions of Hamiltonian, that means they are simply En phi n, okay, or no, let's not write like this. Yeah, so here phi n are energy eigen functions with En energy for each each wave function. So what I am saying is, instead of calculating this trace, you can just find the eigen values of this Hamiltonian operator, okay, and put it in this equation, right? Because you know that if your wave functions can be represented as it can be extended into a eigenfunction energy eigenfunction basis, right? So just calculate the eigenvalue En energy and just put it in this equation. This equation you know, right? This equation you know from the statistical mechanics, classical statistical mechanics. This is valid here also, given the condition that your Hamiltonian you have a energy representation of your Hamiltonian. And this we could have done here also in the earlier problem, like here also, yeah, this we could have done here also. We could have calculated Hamilton. So this is the Hamiltonian, and you can calculate the energy eigenvalues, which will be plus minus mu beta, and then the trace will be just this quantity, okay, which we got from the from this calculation also, from the matrix calculation also. So this is what I am saying, just calculate the eigenvalue for the Hamiltonian, whatever Hamiltonian you have, and you can use this formula for calculating the partition function of a quantum mechanical system. It's perfectly fine. Just give it a thought, you will be able to understand. And this is also, I mean, if you want to go deeper, this is valid only for the systems in equilibrium, because we saw that only the systems which are in equilibrium, they commute with the density operator commute with the Hamiltonian, and the phi n can be eigenfunctions of Hamiltonian or energy eigenfunctions. Energy eigenfunctions. So that means if you have a system at equilibrium, you can always consider this, okay. So you can always expand it in terms of energy eigenfunctions. Is it fine? Do you understand what I am saying, or am I confusing you more? So if it is confusing, just remember, if you are given a Hamiltonian, okay, no matter if it is whatever system it is, if you have a Hamiltonian, just find out the energy eigenvalues and use this equation to find the partition function. That's it, okay. Just give it a little bit thought, you will be able to understand. Okay, so let's go on with the calculation. So we will get gamma minus lambda here, minus delta here, minus delta here, and minus gamma minus lambda here equal to 0. Please let me know if I am doing the calculation correctly. So I am taking the determinant now, okay, minus delta is equal to 0. So we get a quadratic equation like this. Here we have, so this is a quadratic equation in terms of lambda, and we can find out what lambda are. So this lambda is our eigenvalues, right? So this is a quadratic equation, so we can use the quadratic formula, minus b plus minus equal to plus minus under square root b minus 4 ac, right? You know the formula. So you will get this a is just 1 here, c is minus of gamma square delta square, right, divided by 2a. A is just 1 here, so 2, and we can simplify this further. So plus minus 4 gamma square plus 4 gamma square plus delta square by 2, okay. Yeah, and then so the two eigenvalues will be simply, so you just divide by 2, right, and you get this gamma plus delta square gamma square, right, 4 yeah, for this, oh sorry, here you should have 2, right, 448. 4 goes out, 2 gamma square, yeah. And lambda 2 is equal to gamma minus delta square plus 2 gamma square. This is what you have. And then your partition function will be just e to the power minus beta lambda 1 plus e to the power minus beta lambda 2. So you can just simply put the lambda 1 lambda 2 here and you will get your answer. Okay. Okay, is it fine? Okay, so let's go to the next problem. So this is the last problem, and it is also very simple one. Actually, this is I mean, this has nothing to do much with the quantum static. I mean, whatever we discussed till now. This has more to do with, our understanding of what we understood by the probability and statistics. So basically, there is a system, okay, which has two normal modes of vibration, omega 1 and omega 2, okay. And the question is asking what is the probability at any that at temperature T the system has an energy less than 4h omega naught, okay. This is the question. Sorry. So how do you solve this? So first of all, the energy of this kind of system is given by, so you know, it's just a two level system. So the energy is given, I mean, let's consider it a harmonic oscillator, right? Is this fine? And let take omega 1 equal to omega 0, and then omega 2 will be 2 omega 0, right? Because it is given omega 2 is just 2 twice of omega 1. So then your energy become n1, sorry, n1 plus n2, right, plus, so this half omega 0 plus omega 0, so this is 3 by 2 h1 omega 0. Fine. Sorry, this. And so we have to find the probability that energy is less than 4h omega 0, okay. That means so let's consider the possible okay, so that means n1 plus n2 plus 3 by 2 should be less than equal to 4, right? Okay, so what are the possible values? So for this to be happen, so possible values, possible scenario. So if n2 is equal to 0 and n1, so for n2 equal to 0, Okay, let's do one thing. Let's write it more conveniently like this: plus 3 less than equal to 8. Okay, so okay, if n2 is equal to 0, uh, what n1 can be for this condition to hold? 3 is there, so n1 can be 0, 1, 2. If we put 3, then this condition don't hold, right? So these are the possible values for n1. Now this is the first case. Second, if we take n2 equal to 1, then n1 is equal to, so n2 equal to 1 means this is 2 plus 3, 5 is already there, so we can take n1 equal to 0, right? If you take n1 equal to 1, that is okay, 3 to 5 to 7. We cannot take n1 equal to 2, right? Otherwise it will become 9. So this is all the possible case. And then if we take n2 equal to 2, then we already have 7 from here, and so n1 can be 0, and 1 is not valid for n1. Okay, and if we take n2 equal to 3, n2 equal to 3 is not allowed anyway. So these are all the possible solution, right? So the allowed states are basically 0, 0, 0, 1. So n1, n2. So these are allowed states of n1, n2. Okay, 0, 0, 0, 1, 0, 1 can be there, 0, 2 can be there, then 1. So 1, 0 can be there, 1, 1 can be there, and then 2, 0 can be there. Okay, so these are the allowed states. Now question asks, what is the probability at the what is the probability that the system has energy less than this? Now what is the how do we interpret probability? So we know that you know, so probability we studied. So probability to find a system at some energy E is equal to, is given by, you know, this formula, right? Partition function here. This is what we know, correct? And here the question asks, what is the probability you know, that the energy is lower than 4h bar omega, 4h omega naught. That means what is the probability of combined these states, right? What is the probability that all of these system can be in these states? So basically, so this probability will be, you know, uh, the allowed by Q total. Okay, and where the allowed are basically, so let me write the Q allowed. So this is not exactly equal to this, so but you understand, this is basically probability of energy less than 4h omega. Okay, where q allowed is given by, so you take all these values. Okay, sum of beta E allowed, and where E allowed, so the allowed energy is basically this n1 plus n2 plus 3 by 2 h omega naught, where n1 n2 are, these values. Okay, so you calculate this, and you find this, and the total is all the state that you can find, all the possible states. So I mean, this problem has no, you cannot calculate the exact answer, because we don't know, I mean, how many states, I mean, there are infinite, total number of states. So n1 and n2 can go to 0 to infinity, right? But this is how you write the expression for probability of having energy less than a particular energy. Do you understand? Okay, so yeah, thank you. So yeah, today's session got little longer, uh, sorry for that. So I hope you guys understood everything, and please let me know if you have not understood some particular thing, and I'll try to explain. Or if it is fine, you can we can close the session. So is it fine? And yeah, we can meet next Saturday same time. Okay, so thank you guys for joining. See you. Bye.